Lesson 1, Example 1. We are solving differential equations. To solve a differential equation means to find a function that has a given derivative and a given condition. In this case, though, we have dy dx equals negative x over y, and then we have the condition. These are a little bit different, and I don't know if you can see that right away. They are different in the fact that the slope does not depend only on x. The slope, dy dx, of our function that we're going to find depends on the x and the y. So here's what we need to do. The first thing we need to do is separate the variables. And what that means is to get the y's and dy's on one side and the x's and dx's on the other side. So you might see here if I multiply both sides by y and simultaneously multiply both sides by dx, I get this form of the differential equation. See, I have y's and dy's on one side and the x's and dx's on the other. Another way we could have done that was simply cross multiply. I'm going to write this again, and if you would write it again in your notes, you'll be able to follow your work later. The next thing I'm going to do is integrate both sides. First, I will start with the left-hand side, and the integral of the left-hand side is y squared over 2 plus c, but I'm going to hold that plus c for a moment. I'm going to do the right-hand side, which is negative x squared over 2 plus c. Now, had I written a plus c on the left-hand side, I would have brought that over and they would have combined to get one gigantic plus c on the right-hand side. I'm going to go ahead and multiply both sides by 2 and also get the y and x's on both sides just to make a point here. Y squared plus x squared is equal to c. This is what's called a general relationship. It describes how y and x are related in an effort to get dy dx to have this derivative. But what we desire is a function answer, a particular solution that has the derivative as shown and the condition as shown. So what I'm going to do now is solve for y. So I have y squared equals c minus x squared. I'm going to take the square root of both sides, and I end up getting absolute value of y equals the square root of c minus x squared. So that's going to result in two different answers. I get plus or minus the square root of c minus x squared. So I have a circle, and the circle can be described by two different functions. Square root of c minus x squared, and also negative square root of c minus x squared. So those two pieces together will give us the circle. So the circle is a relationship, and it is defined implicitly with two different functions, positive radical and negative radical. We have to decide, is it the positive radical or the negative radical, because I am looking for one function that satisfies the differential equation. And we get that information from the conditions described in the beginning. The fact that y has to equal negative 3, that alone tells us that we're looking at the negative radical. So I would say that negative 3 equals plus or minus, but it has to be the minus version because I have to get the negative 3. C minus, and then I plug in 4 for x, and that gives me 16. From here, 3 equals the square root of c minus 16, and I conclude, therefore, c has to equal 25. So my solution to the differential equation, y equals negative radical 25 minus x squared. Again, that's the bottom half of this circle, which contains the point 4, negative 3. And this solution that we found here is called, if you remember from before, the particular solution. Example number 2. This time I'm looking at Lagrange notation. The slope of some curve is f prime of x and y. Notice again that the slope depends on x and y. To solve these, though, I prefer to use Leibniz notation. So I'm going to say dy dx equals xy over 8. First step, do you remember? We're going to separate the variables. What will that look like? Well, it's going to be dy over y, see I'm dividing y both sides, equals x over 8 dx. There I have successfully put the y's and dy's on one side and the x's and dx's on the other. As a general rule, I think you will find this helpful, that if you've got a coefficient, in this case the coefficient of 1/8, let's leave that on the x side. Okay, I'm going to rewrite it again so that I can follow my work later. And I am going to integrate both sides. On the left-hand side, I get the natural log of absolute value of y equals, and that's going to be x squared over 16 plus c. This defines the general relationship between x and y, an effort to have the derivative described in the very beginning. Okay, but as you remember, we want to solve for y by itself. So let's come up here to do that. I'm going to exponentiate both sides. Now look where I go with this. I'm going to say that the absolute value of y, because e to the natural log returns itself, and then this is going to equal c e to the x squared over 16. That's generally the very next step, and you may be wondering, okay, wait a minute, what are you doing with that, and how come the c is out in the front? So I want to describe that. I'm going to do it in a different color because I normally do not show this. You're going to get used to doing it so many times you're going to understand it. But let's start off with this here, x squared over 16 plus c. Let's make this a little bigger. Okay. Again, if I exponentiate both sides, the e and natural log cancel out to give me absolute value of y. And then this is going to be e to the x squared over 16 plus c, all of that in the exponent. One of the important features of this unit is the careful placement of c. In earlier units, c was just tacked on at the end of some polynomial, but now c gets special consideration due to its location. And if you see here then that the absolute value of y, I can write this as e to the x squared over 16 times e to the c, properties of exponents. And then e to the c is just some other constant c. And that's why I then bring that constant out front. Let's continue. Now what I want to do is I want to get rid of the absolute value. So I'm going to say y equals plus or minus c e to the x squared over 16. This is an important part. The plus or minus c value is just some other c. We're going to solve for not what is plus or minus. We're not making that decision here. We're solving for the coefficient that comes in front of e to the x squared over 16. So in effort for us to not get confused with that, I changed this circled value, plus or minus c, to something that I like to call c star. It's just a reminder that it's still a constant, but it's a little bit different, and it incorporates the plus or minus. It's finding the value of c star that will make this thing work. So there we go. Now I have to use a condition, and it says that when x is equal to 0, y is equal to 5. So 5 equals c star e to the power of 0. Great. E to the power of 0, that's easy. E to the power of 0 is 1. So therefore, C star equals 5. I don't know if that makes sense to you. The other way we would have said that is plus or minus C equals 5. And the plus or minus C gets plugged in to the front here. So now we're going to say that y equals the thing we solved for in the front, which is 5, e to the x squared over 16. And then that is the solution to the differential equation. I hope I didn't confuse you with the C star. We are going to use C star in class. Another way that people have done this, instead of saying plus or minus C, instead of writing C star, they just make it a different value, let's say M or K or some other value to represent a constant. Example number 3, I'm going to quickly convert this to Leibniz notation, dy dx equals, I'm also going to write this so that it's easier to separate the variables, e to the x, then I'm going to write over e to the y, properties of exponents. When I separate the variables, I get e to the y dy equals e to the x dx. I am then going to integrate both sides. Okay, the integral of the left-hand side is e to the y. The integral of the right-hand side is e to the x. And then we combine the c's to get plus c. This is my general relationship. The effort now is to solve for y, and we have to pay particular attention. We have to have particular care in our placement of c. To get y by itself, I'm going to take the natural log of both sides. So the left-hand side is going to be y, and the right-hand side, be very careful here, is the natural log of e to the x plus c. Please don't fall victim to this. The natural log of e to the x plus c is not equal to the natural log of e to the x plus natural log of c, nor is this the multiplication. There is no property for the natural log of a plus b. I had to take the natural log of the whole side, and that I will. I'm ready to use the condition. So the y value is natural log of e plus 2, so natural log of e plus 2, and then I have to substitute 1 in for x, and I can see quite clearly then that c is equal to 2, and the solution to my differential equation, y equals the natural log of e to the x plus 2. That is my particular solution. Example number 4. Let's get right to work here. You're going to notice there is no x, and the only thing that I have out in front here is a coefficient, and if you remember, we want to leave any constant coefficients on the x side. So here I have dy over y equals 5 times dx. I'm going to integrate both sides. Natural log, absolute value of y equals 5x plus c. General relationship here. I'm going to exponentiate both sides. So the absolute value of y equals c e to the 5x. Again, do you see that? I don't want to keep saying it, but e to the 5x plus c would equal e to the 5x times e to the c, which is c times e to the 5x. That's a move we're going to use so often. I'm confident that you will master that quickly. Okay, next, I'm going to get rid of the absolute value by saying y equals c star. Yes, y equals plus or minus. I tend to skip the plus or minus and get right to the c star. E to the 5x. Now I'm ready to plug in the condition, and y is 9 when x is 0. Therefore, c star equals 9, and the particular solution to my differential equation is 9e to the 5x. Example number 5. Okay, let's get right to work. dy over 6 plus y equals 4 dx, my separation of variables. Integrate both sides, which leaves me with the natural log, absolute value, 6 plus y equals 4x plus c. I exponentiate both sides, absolute value equals c e to the 4x. Then I have 6 plus y equals c star e to the 4x. Bring that over here. So now y is equal to negative 6 plus c star e to the 4x. Plugging my condition, 9 equals negative 6 plus c star e to the 0. Therefore, c star equals 15. And then I have the solution. Y equals negative 6 plus 15 e to the 4x. The solution to my differential equation. Okay, here we go. Example number 6. So now I have dy over 5 minus y equals 1/3 dx. That is a successful separation of variables. I'm going to integrate both sides. Please be ultra careful here. I should have you do this without my assistance first. The answer is not on the left hand side, natural log absolute value of 5 minus y. If you did that, then you missed a critical u substitution. See, if I let u equal 5 minus y, where can I put that? U equals 5 minus y, then du equals negative dy, and dy equals negative du, and I'd have to pull out a negative. So be careful with that. That's going to be a negative natural log absolute value of 5 minus y. That's going to equal 1/3 x plus c. The first thing I want to do here is get rid of that negative, so I'll multiply or divide both sides by negative 1. When I do that, I get negative 1/3 x, and I can keep it plus c. Now when I exponentiate, absolute value of 5 minus y equals c e to the negative 1/3 x. Get rid of the absolute value. 5 minus y equals c star e to the negative x over 3. I'm going to solve for y, so now y equals 5 minus c star e to the negative x over 3. With my condition, this is 8 when x is equal to 0. See, that's a nice move that keeps coming up after and after and after, or over and over and over. And based on this, we can say that c star is equal to negative 3. So y equals 5 minus a minus, so plus 3 e to the negative x over 3. This is our particular solution to the differential equation.